Okay, so I think not everybody, most of you probably familiar with this average. This is average over a sphere centered at the x and the radius t. Okay, and then this is a normalized surface measure on the unit sphere, and then the spherical maximal function, and also in 2 dimensions, this is circular maximal function that is defined as a supremum of this average. Okay, this is called circular in 2 dimensions and spherical in higher dimension. This famous theorem, which is to Stein and then later Bourgain in 2 dimensions, that is a theorem which tells the maximal function is bounded on LP, and if and only if p bigger than d over d minus 1. So because this maximal operator is the dilation invariant, so this is the only pair of PQ you can have maximal bound. Okay, this is actually complete characterization of LP boundedness of, or even LP LQ bound of the maximal function. Okay, so it's very satisfactory result because we completely understand the mapping property of the maximal function, and also at the critical exponent. I wanted to explain a little bit in detail what happened at the critical endpoint case, because the title of my talk is endpoint, right? Estimate. So at the critical endpoint, Bourgain he proved the restricted weak type bound when dimension bigger than or equal to 3. Okay, so the restricted weak type means this is a Lorentz space. It's a weak LP space, and this is a restricted space. Maybe you can replace F with a characteristic function of some measurable set. Okay, just then take L d over d minus 1. Oh. Then he proved then this result almost sharp in this sense. So this cannot be bounded from any Lorentz space. Second exponent are bigger than 2. So from this space to a weak space. So this only the 1 here is the only space you can get the maximal bound. Again, this can be easily shown using this kind of function. If you test the inequality with this function, then this function is contained in any Lorentz space R bigger than 1. But the maximum function is infinity. Even the supremum is taken over compact interval, not in whole interval. Compact interval, you can show that. Okay, then in 2 dimension, this p become 2. At that particular exponent, even restricted weak type also fails. This can be shown using Kakeya set, actually Peskovich set. Okay, but in the earlier Lockband, he showed, but for the radial function, this actually holds. Still, restricted weak type is true. Okay, so so this is classical result, and but later people wanted to think about more general set of dilation set. Now we consider just a general set contained in the interval and define the maximal function in that way. So dilation set now generalized. Okay, so maybe it's probably that this maximal function may have a better bound because the maximum is taken smaller set. Okay, and also, but in the previous slide we considered the maximal function in the whole line, but it's enough considering this compact interval. Then you can use Ritzel-Paley and the dilation argument you can put together, you can recover LP bound if you have LP maximal bound for that. Okay, so, and also if you also can think about PQ bound in global setting, taking soup on whole real line. In that case, you have to satisfy this sort of scaling condition of LP and AQ. So for that case, you probably need some parameter T power in front of this maximal function. It's necessary to get this global bound. But anyway, today I just want to talk about the maximal function defined on dilation set contained in unit interval. This interval 1 to interval. Okay. Okay. So then we wanted to determine pair of exponent P and Q, which allows this LP AQ bound for the maximal function. It's clearly, I mean, this pair will depend on the size of E and the certain property of E. Okay, so actually the smallest possible set is just a singleton, right? Just the 1 point. 1 point is in that case, it's already started many, many years ago. And the Littmann, and this has become just a convolution operator, a convolution with the surface measure, okay, just with the radius A, right? Then this function, not really maximal function in this situation, is just a convolution operator. In that case, this is bounded from LP to LQ, if and only if this 1 over P and 1 over Q is contained in a triangle given by this 3 point. Maybe I can draw where is okay. So this is the axis of 1 over P, and this is the axis of 1 over Q. And this is 0. 0 actually, I mean, corresponding to L infinity space. Okay, so 0, 0, and 1, 1. And we have another point here. D, and this actually sitting on the line of duality. So that means that this anti-diagonal actually 1. So in this triangle, this convolution operator is bounded. Okay, so and actually the upper triangle, it is impossible because of a translation invariance of the maximal operator. Okay, so okay, then this is the smallest possible dilation set, and then another extreme case is the whole interval. So now we have a maximal function defined by dilation, which is given by whole interval. This in that case, Schlag and Sorg, they obtained the result, which tells this maximal function is bounded on the this becomes triangle when dimension is 2, but 3 dimension is quadrangle. So 2 dimension is a triangle, in the 3 dimension is quadrangle, because these 2 points become same when dimension equal to 2. Okay, so they proved when 1 over P and 1 over Q is contained in this quadrangle, okay, then the interior of the quadrangle given by this 4 point, and including this diagonal line segment. It's just a consequence of interpolation. So then also they showed this maximal bound only possible except this line. In this convex hull of this 4 point, except this line, you can show the only LPLQ bound possible. along this line, actually LP-LQ bound is impossible. Only a weak type bound is possible. Okay, so that, but they only show the necessary condition. But later, I mean, that remaining part was considered by myself long time ago, and I managed to prove the restricted weak type point when for the Q3 and Q4 when dimension is bigger than y equal to 3. So in that case, we have endpoint case. If then interpolation, we get the borderline case. And along this line, you can get the restricted weak type, just interpolation with a Bulgarian result. Okay, so then also the LP bound actually fails because of that example, which I showed in the beginning of the talk. Okay. So, and but in 2 dimension, we have restricted weak type at this point. But with some technique, which I will show you later in this talk, we can recover LP. We can prove LP bound all the way because we don't have any bound here in 2 dimension, but we have restricted weak type bound here. If you interpolate, you cannot interpolate because you don't have an estimate there. But with some bilinear technique, you can prove LP-LQ bound here in 2-dimensional case. So yeah, now the maybe the one problem just left open in a sense of LP-LQ bound this point when one of P and one of Q is equal to Q4. At that point, the LP-LQ bound is remaining open. Okay, so it's one open problem. And then now I wanted to move to more general dilation set. So to quantify the size of dilation set, we need to consider some proper dimensions. So here this notation, any delta means the minimum number of open interval of length delta required to cover set E. Okay, so this is that is actually comparable to maximally delta separated subset of E. Number of maximally delta separated subset of E. Okay. Then the upper Minkowski dimension is defined as infimum of A, which is satisfying this inequality. And also this upper outside dimensions is defined in this way. So here, this definition is a little bit involved, but the idea is quite clear. So this definition is very similar to the Minkowski dimension when interval length is 1, but it's actually taking into account that the size of the set E. So it has a very nice scaling invariant property. You can scale it, but still these quantity never change. Basically, the remaining constant does not change. It has a very nice scaling invariance property, actually. So then the infimum defines the outside dimension of the upper dimension. So these 2 dimensions we will use to study the maximal function. Okay, and then obviously this outside dimension is more restrictive, so this inequality is clear. Okay, so yeah, to describe the LP-LQ bound, we need some notations. So here, yeah, you don't really have to memorize this, but this one is on diagonal, and when mu is equal to 1, it actually matches with the endpoint case of a spherical maximal function, and this point is lying on the line of duality. So line of duality usually easy to prove estimate because this is between L2 and L1 to infinity bound, right? It's very convenient place. Okay, so and this guy will be a problem, I think. But more difficult to prove some bound at that point. But now we denote the convex all of these 4 points as Q mu alpha. So So this interesting feature of this is that these are completely determined by Minkowski dimension, and this guy related to Assad dimension. Okay, so then this was started. These four guys already 5 years ago, more than 5 years ago, definitely. So they proved this maximal function with the mu Minkowski dimension and the alpha Assad dimension. This is bounded from LP to LQ when one of P and one of Q is contained in this set, right? And when dimension is bigger than or equal to 3. And 2 dimension, they managed to prove when alpha is relatively small, smaller than or equal to 1/2. Then later, more involved case was proved, more involved case with in 2 dimension, alpha is bigger than 1/2, obtained with Sieg and Roos. Okay. And this they also showed that this result is really sharp. Constructing certain specific dilation set. Okay, and more recently there are results with very specific input functions. So when they actually Bertrand, Roos, Seeger, and Zhao, this is one of the author of this paper, and they consider the F contained radial function, and then try to characterize the LP-LQ bound from with the general dilation set. Okay, and also in the radial case it's much easier. So they prove they also proved many endpoint case. But in this talk I don't want to provide the detail about that. I just want to concentrate on the general function. Okay, so then the natural question is what's going to happen for the endpoint case. So we have a bound on this region, and there is some borderline case. We do not have the maximal bound. Okay, so but that's just dimension concept. Dimension is defined by infimum of a certain quantity, right? With that definition, we cannot get in endpoint case. So we have to impose a more quantitative control of the dilation set. So this is the concept. So we say the set E has a bounded mu Minkowski characteristic. If this is bounded, that means the size of this maximally delta separated set is controlled by delta to the minus mu, right? Constant time, something like that. And also E has a bounded alpha outside the characteristic if this quantity is bounded, right? Okay, so under these conditions, these four guys also obtained many of the endpoint case. Okay, so so when E has a bounded mu Minkowski characteristic, okay, then this is a restricted weak type. When one of P and one of Q are equal to these 2 points. Okay, and they also proved the corresponding endpoint for the Assad dimension case. Okay, but only for this reason when P alpha is between 0 and 1/2. Okay. Okay, so once you get this, I mean, endpoint, then you almost complete the picture, but you're missing 2 points. At that point, it does not have LP bound, right? You only have a restricted weak type bound. At that point, still actually open as it was open in the case of a circular maximal function, and also spherical maximal function. Okay. So then one of the main results of this talk is the proving that missing endpoint in 2-dimension case. Okay, so then it's better to write a more concrete way. So in two dimensions, this exponent, this point is given by this. So this actually provides a complete solution to the restricted weak type bound at the critical point. Okay. So then why we have to use a dimension? So this is not difficult to show. It's kind of scaling argument combined with some sort of naive type example. Then you can use that. Then you can prove this inequality. And so this is the function is adopted a very small arc, and then you scale it with the length of the arc. Then you can prove this inequality. The LP to LQ, Lorentz space bound is controlled by, has a lower bound like this. Okay. So in particular, if you have this endpoint case, then all the exponent simplify in this form. Okay. So then if this is bounded, then you definitely have a bounded outside characteristic. So the bounded outside characteristic is natural assumption to get the endpoint, especially restricted endpoint bound. Okay, so have any question? Okay, so and I continue. So it's pretty much well understood, right? When we're studying the circular maximal function, especially because circular maximal function, you don't prove the desired maximal bound simply using the Stein classical argument. So local smoothing of wave operator plays an important role, right? So similarly, this wave operator is very close, very much related to the spherical average. So our result was related to the smoothing property of wave operator. So this is the wave operator, and this is a standard little Paley decomposition. And then we wanted to study sort of a discretized local smoothing estimate. So here the E delta denote a maximally delta separated subset of E. This is our notation, and we impose this set has bounded alpha outside characteristic. Then you consider this form of inequality. This is a bit different from the usual local smoothing estimate because in the typical local smoothing, we actually integrate along T on over interval. But here, T discretized depending on the size of frequency. And when we're considering this PJ, the frequency with the size 2 to the J, we consider the 2 to the minus delta separator. So this actually matches with the uncertainty principle, right? And we wanted to start. This actually will give correct LP-LQ bound for the generalized maximal function with the general dilation set. Okay, and of course, this S, this is a regularity parameter, will depend on P and PQ and alpha, right? So, so our result, endpoint result will be a consequence of a sharp local smoothing in this form. Okay. Okay, so there is some numbers, some regularity exponent. I put so also you don't have to memorize this, but it'll be complicated. There are many exponents. Okay, then the maximum of all this regularity exponent is the SC, that's critical exponent. Okay, so then first step is, how much regularity is required to get the estimate, the discrete local smoothing estimate. Okay, so if you impose the bounded outside characteristic, then and also if this inequality hold, this has to be, the regularity exponent has to be bigger than this exponent. Okay, it's not difficult to show. I mean, the first one, okay, the first one. This one can be shown the sort of fixed time estimate. That means you can consider the large frequency cutoff function and putting it and test the this inequality with that particular function. And you don't need, I mean, many of these. It's just only one t is enough. You can prove that. And this one is a bit related to some sort of lab type example. Okay. Okay, so then to show this, probably you have to use the asymptotic expansion of wave operator. Okay, so then if you compare these three exponent, right, then which one dominating in which region? So in this is the anti-diagonal, which is called line of duality. On this region, this S3 is dominating, and in this region, in this region, see, S2 dominating. It's a simple computation. Okay, so then the S1 is the 1OP and 1OP. Yeah, this S1 is dominating in this region. Okay. So also when alpha is equal to 1, this exactly matches with the local smoothing conjecture for the wave operator. Maybe local smoothing conjecture in PQ setting, not an LP setting. Okay, so only LP setting. Actually, maybe you are familiar with local smoothing along this line. Definitely, there is some local smoothing conjecture can be formulated on this diagonal or so in this region or so. Okay, so then there is some easy estimate we can prove with the known fixed time estimate. This is due to Miyachi and Peral. Maybe Miyachi proved the endpoint case. Okay, so then we just have a 1t here, and then this estimate is true. Okay, so with the S1, yeah. Then because in then when this S3 is dominating, when this dominating, right? Then we don't need a complicated local smoothing estimate. We only need a fixed time estimate. Then count all the delta separated, 2 to the minus zeta separate set, and that gives the sharp result. So nature of smoothing is quite different. Here is everything, every possible smoothing actually achieved by fixed time estimate. That means decay of a spherical measure is good enough to recover all the possible smoothing estimate. But these two regions is a bit complicated. But in a point of view of interpolation, right? Once you get a sharp bound here, because these two conditions, these two regularity assumptions actually coincide along this line. Once you get the sharp bound along this line, then you will recover everything by interpolation, because you have a bound here, sharp bound already got from fixed time estimate, and the bound here also trivial because you're dealing with the L infinity bound, right? Then only thing you have to do is just proving sharp bound along this line, then you will recover all the, you can prove all the sharp smoothing estimate. Okay, so so then maybe the conjecture is that this is the critical line which I showed you, and the E has bounded alpha sorry characteristic. Then we claim this estimate hold. Okay, that's a natural conjecture. Okay, so then this is the endpoint case also. So there is a couple of remarks, and so I mean, if you think about fixed time estimate, as I already told you, this regularity exponent is the fixed time regularity. But here you have, I mean, many of delta separated. This is that means this kind of different time, right? These guys actually sort of interaction. Maybe still, I mean, you can keep the fixed time estimate. That's a key. And also, definitely, if you have a classical local smoothing over the whole interval, right, then you can recover it. But the important thing is the range. Range actually expanded because when your alpha getting smaller. So in an extreme case, when alpha is equal to 0, then this line becomes this. You see, this alpha is equal to 0, then this becomes 1/2. The line becomes this. So in that case, it's much easier to prove. Okay, so and the endpoint case, you need extra regularity here, and also this was verified for the reason p between 1 and 2. These 4 guys, and also Hiller did something with epsilon loss. Okay, so then to prove this endpoint case, we need something beyond the L2 theory. So this is our result. Is along the critical exponent, we get the sharp discretized local smoothing estimate with this condition on Q. This Q is very complicated. So, but still, this is better than, way better than the something you can obtain with the L2 estimate. L2 means the L2 here. Okay, but this is not the best possible result I can state, because if you allow a little bit of loss, you can expand the range a little bit further. That means you can interpolate some estimate, some local smoothing estimate along the diagonals, and you can extend the range. Okay, and also the sharp bound also available on a wide range if you use this result. Yeah, they proved the local smoothing estimate, sharp local smoothing estimate without loss of any regularity. So, but anyway, for our purpose, this is good enough. Okay, so then once you get that estimate, you can prove the endpoint. Actually, I wanted to explain how to prove that. So here, this is standard decomposition. And yeah, this is P0 is a trivial regularity exponent. So you don't have to worry about that. And then we decompose the function in that way, and then the maximal function is controlled. This can lead of the low frequency part. That is actually controlled by the maybe a very simple because the function very rapidly decaying, maybe Young's convolution inequality is good enough to control that part. Okay, so then we wanted to prove a restricted weak type at this particular point. Okay. Then this particular point actually goes through this critical line, which appeared in the theorem. This is the critical line here into dimension. Okay, so then if we prove this, okay, then this Q is actually the critical Q. So you have a negative power when Q smaller than negative power when Q bigger than this number. Bigger this number, and smaller than positive power, right? So you have some sort of positive and negative exponent, and naturally match with some sort of interpolation theory. So if you interpolate, then you definitely get something better than this. This is can be done by Bulgang's summation trick. So this is a nice trick whenever you try to sum something, but in a slightly weak function space, like a weak space or restricted weak type estimate is available. So this exponent is natural. If you have some sort of positive and negative between these two exponents, two set of exponents, then when this exponent disappear by interpolation parameter, then you can get restricted weak type. So once you get this inequality, then you get restricted weak type. Okay. Then how this local smoothing plays a role to prove that sharp maximal bound with the frequency localization. Okay, so this is well-known asymptotic, and then this, yeah. So because we have a local frequency localized function, so these two guys are compatible when t is very small, 2 to the minus j. This is we believe this is true always, right? But have to justify it in a suitable way. Okay, so there are several ways to justify it, but maybe you can use Fourier series to expand, and then that will give some sort of a translation vector, lots of translation vectors, but with the rapidly decaying coefficient. Okay, so then if you believe this, actually this inequality is not really true, but if you believe this is true, so trivially this can be controlled by this, right? Because this is maximally separated. You have an E, and you have a maximally separated by 2 to the minus j point, right? Because of this heuristics, if t is close enough, t are compatible. So each of the separated point set will control the whole supremum, right? So this inequality trivial. Then we upgrade with the control that with LQ norm. Then maximal function is bounded by this. Okay, so then if we use the local smoothing for discretized dilation set, yeah, we get this. Yeah, that's how we prove this. Okay, so then I have a 6th slide. So, oh no, 5 slide, right? So yeah, I will be brief. How to prove that, to show how to prove that. Okay, so this is a little bit of a generalization of the estimate, which appeared in the previous slide. So we define some sort of a constant. This constant is depending on delta. Okay, then we take another supremum here, and this quantity will needed to carry out some sort of induction argument. Okay, so then just to consider general delta separated set, and the function is function has frequency localization like this, and then we prove this inequality. So basically same inequality, but we impose some sort of uniformity on the set, separated set. Okay. Then how to prove this? Then we use a scaling, rescale everything to. This is a very high frequency, right? Then we rescale it with the uniformized constant. Okay, then we reduce a small frequency. Okay, for that we have to consider this extension operator. So here the G is supported on analysis with a size 1. Okay, so then we consider this collection of interval, unit interval, but that number actually mimics sort of other dimensions. So it has some sort of, if you consider this interval of length R, then the number of intervals contained in this interval controlled by the size of that interval, so R to the alpha. Okay, it naturally appear when you rescale the estimate. Okay, so then still you can keep all the constant uniform under the scaling because of this kind of simple redefining the constant. Okay, so then what you do is we prove restriction estimate, bilinear restriction estimate with the separation condition for this guy. So this is an angular set. This is a set on the unit sphere, and yeah, we prove this sort of bilinear restriction. Actually, bilinear adjoint restriction estimate. So this A1 is the analysis analyze away, maybe away from 0 with distance comparable to 1. Okay, then these two supporter function is separated in angular sense, then we can prove. You can see this actually match with Tom Wolf's result when alpha is equal to 1. Okay, but the range become wider as alpha goes to 0. Okay. Okay, so maybe I have to finish, right? So the idea is using some sort of induction argument, but this we don't believe this is optimal. So if you use a standard, example, then the range is this, but the theorem actually does not give the up to this end of this critical exponent. Okay, then once you get the bilinear estimate, then you have to get small scale bound. That means small angular separation. There is something called the Whitney type decomposition, and you combine this with the bilinear technique, then you can prove this sort of bound. This is optimal bound. Okay, then you can prove you have a bound here because of this bilinear estimate, and then how we can prove the a sharp bound, because L1, L infinity, right? The sharp bound is almost trivial. But here, when you're away from this region, right, that's local smoothing, available local smoothing, it typically doesn't, actually has a loss of, epsilon loss of regularity. So if you interpolate, you cannot get the sharp bound. Then you cannot get the endpoint estimate for the spherical or circular maximum bound. So the safe place is here. Then we interpolate, then you get, and you use a Fulgang's summation trick again, then you get the restricted weak type bound at this point. Okay, so yeah, that's it. That's the idea how to prove the sharp local smoothing for fractional dilation parameter. Okay, thank you.